Can somebody in this room tell me what the heck this thing is going to look like? And of course, for things to be defined, you know that A is going to be a 2 by 2 matrix. What happens to V bar? Why are you shrugging your shoulders? Because you don't know what the matrix A is. So I think the matrix A could transform this into any other vector in R2. Do you guys agree? I have no idea what's going on. It could do that. Do you see my point? But what if, here's the x-axis, here's the y-axis, here's my V bar. Wouldn't it be interesting if I had a vector V bar that had the quality? When I multiply by a particular matrix A, I get a scalar multiple of V bar. In other words, what if multiplying V bar by A just simply gives me another vector in the same direction? Can you read my sloppy writing? Now that'd be interesting.
Is that lambda?
It is a lambda,
Okay.
yes. And I'm kind of nervous today in class. I'm going to talk about the mechanics of this. And then you and I and the author, we're going to drop it like a rock. Until I start to talk about solving systems of differential equations, I'm going to come back and use these particular notions. And we'll put them to great, great use. What I want to do right now is just play with this. If I have a matrix A that has a corresponding vector V bar and a corresponding constant lambda that have this quality, I sometimes classify the vector V bar as an eigenvector. And lambda is a corresponding or associated eigenvalue. You guys, I don't speak German. Does anybody else speak German? Do you know what the word eigen means? Because I've been honest.
No.
Someone told me once, I forgot. But it made sense when somebody told me.
Where's
I have no knowledge whatsoever of German as a language.
no Alex
No one?
today, or else he'd look it up.
Yeah, good point.
Yeah.
So everybody, look at the consequence of having an eigenvector V bar. I think I can rewrite this in the following fashion. Yeah, oh wait.
So we're not talking about the transformation A such that V bar is always transformed to lambda.
If you want, you can.
We could, but more generally, what we mean is the particular vector V bar such that for
Better.
any given A,
Better. For a given A, matrix
For
A, there is an existing eigenvector V bar such that transforming V bar is nothing more than a scalar multiple of V bar.
is going to be unique. If it's not that first form he said, is it going to be unique?
Is what going to be unique?
The eigenvector.
For different eigenvalues, the eigenvectors will be distinct. But for a given eigenvalue, I might have more than one eigenvector. And how many eigenvectors do I have? Well, it depends on what the dimensions of A. And whether or not something funky goes on along the way, which it will. I'll force it to go funky along the way. We'll have to deal with it.
So, according to Google Translate, it's
Oh, thank you.
its own peculiar, inherent, proper, individual, particular, separate, strange, possessive.
Really? It's not what I remember. Strange? I think it's beautiful.
It's also a part of the C++ library.
Is it really?
Yeah.
Well, I guess it should be, because if you're using C++ to solve systems of DEs,
Yeah.
I can see that. Can you do it one more time, Daniel? Sorry. Thank you. As you're eating, I apologize. So the word eigen is own, peculiar, inherent, proper, individual, particular, separate, strange, possessive. I like the word own, because A being multiplied V bar sends it to itself. Well, a scalar multiple, but on the same line as the original vector V bar. I kind of like that. I think that's pretty good. Thank you. Oh, by the way, if I factor out a V bar, does that give me this?
Can you do that? Yes.
Good, good point. I don't think it can.
You can.
I can't take a matrix and subtract a constant together. So I think what I need to do first is come in here and say, well, you know, the second term, can I think of lambda times V bar as, how about lambda times the appropriate size identity matrix times V bar? Now when I pull out a V bar, things make sense. I'm subtracting two matrices of the And for me to find the eigenvalue, I'm going to go ahead and look at how this is a true statement. So, formal definition, given a matrix A. V bar is said to be an eigenvector if it satisfies this condition and is a non-trivial vector. It's not the zero vector. And lambda is its corresponding eigenvalue. But if V bar is a non-trivial vector, if it's a non-zero vector, then for this particular left-hand side to be equal to 0 necessarily implies that A minus lambda times I is equal to 0. That's so important. Can I give it a name? Everything I see inside my circle, I sometimes refer to as my characteristic equation. I sometimes will even refer to what's above my red brace that's set equal to 0 as my characteristic polynomial. You guys, now that I'm looking at the board, I think I've got two mistakes that I did not mean. I'm being sloppy. Chris?
I'm sorry, before we go on, I thought we said that there is no zero product property
For what?
matrices. And also you forgot your bars.
Thank you. That was my mistake. Not only did I miss the bar here, but I forgot to put it up here.
But I'm not sure how you can jump to the conclusion. Easy.
Because V bar is not just a standard matrix, it's a one-dimensional matrix. And since it's only a vector, I've only got one dot product in there for that column. And so I think when it comes to one-dimensional matrix like V bar, if that's going to be a non-zero vector, then this out here, which by the way is just a scalar expression, I think it has to be equal to 0. Because what you see right here is not necessarily a vector. I think what this is going to give me is just a scalar multiple V bar. Because in the end, it isn't going to just be a scalar.
Is it because also maybe you could look at the 0 bar being V bar times 0, and then both are being multiplied by V bar?
Unfortunately not, because that means I'm going to say that V bar is equal to 0 bar, therefore the scales are equal to each other. It sounds like I'm saying that, but technically speaking, V bar is not 0 bar. Unfortunately.
Is it not a legal operation to add lambda times the identity matrix to both sides? Because that would give you something really strange.
What do you mean it'll give me something strange?
It would imply that the matrix A is lambda times the identity matrix. If you added lambda.
And what's wrong with that?
Because we want to find a. I don't.
No, I'm being honest with my question. I'm not trying to trick you.
I'm sure there are other matrices out there that have eigenvectors that aren't just a scalar applied to the identity matrix.
But I think what you see inside my circle, my big black circle, if you force yourself to look at that equation, you're going to be able to solve for whatever lambda is. Let me give you an example.
So if I could just ask for some clarification here, we're using the identity matrix as kind of like a math-y sort of thing for a funky looking
placeholder.
form of 1.
Well, yeah, because I
Okay.
want to be able to, after I factor out a V-bar, get something in my parentheses that I can actually talk about. And if I don't think of this matrix as itself times I,
Yeah.
then once I pull out the V-bar, check out how nonsensical this is. I can't take a constant lambda subtracted from a matrix. It has no meaning.
But that's why, so it's, the identity matrix would just be like a funky looking form of 1. That's why it's legal to
Yes,
put
and
that in there?
And it allows
Okay.
me to talk about what's inside the parentheses as
Okay.
as another matrix.
Okay, cool. Well, yeah, I see that.
And I think, technically speaking, so Chris, going back to what you were saying, technically speaking, it is true that this doesn't necessarily have to be a 0 vector, but what is true? Oh, I messed it up, hold it, that was an A. What is true is that the determinant of that particular matrix has to be equal to 0 numerically. That has to be true.
Well, I don't know why that's true. Could you please explain that?
Sure, I'll prove it to you. So can I make a big loop from here to here? Given that these two matrices are equal to each other, I think this has to be true.
Parentheses.
Oh, but the determinant of, I missed a parenthesis, sorry. The determinant of the product of two matrices or vectors is the same as the product of their determinants. Does everybody see what this matrix looks like? Everybody.
Not really.
Yeah, I
No.
don't either. It's not a matrix,
Scalar.
it's just a real number, a scalar. And I think on the right-hand side of the equal sign, the term is 0 bar is going to be 0.
Oh, so I see.
But if v bar is not the 0 vector, then I think that scalar over there is going to have to be equal to 0.
So that's where we can use the 0 bar property.
Well, yeah, because now, like you just admitted, I'm dealing with real numbers. So I think this is going to be my characteristic equation. There's my characteristic polynomial. And, as an example, you guys, I can't create some examples in class today. Off the top of my head and not waste our time, I apologize. I made some examples up last week when I wanted to discuss this, and I've got them right in front. So I think for me to find the eigenvalues and the corresponding eigenvectors for this matrix, life's going to be a piece of cake. It's my first example. So I'm going to probably write way too much on the board. I'll start skimming on this with my subsequent examples. Let's compute, or generate, I should say, the characteristic equation. I think if I were to look at the determinant of my matrix A, which I can't write, minus lambda times I, where I is the appropriate size identity matrix, then this is simply going to give me 3 minus lambda 2, negative 1, negative lambda, being equal to 0. Bottom line, you guys, the determinant A minus lambda I simply takes lambda and subtracts it off the main diagonal. That's all it's doing. It's just if I try to value this 2 by 2 determinant, doesn't it give me lambda times lambda minus 3 plus 2? Which means lambda, jeepers, I don't know, you guys help me with this. That's lambda minus 1 times lambda minus 2. Is my math okay? So I think lambda, I'm running out of room. Can I? Well, I'll just come over here. So you guys help me with this. What did I just find? Lambda was equal to, I think, 1. Is that true?
1
or
or
lambda is
2.
equal to
2.
2. Thank you. Now, for me to find the corresponding eigenvectors, I think what I'm going to do is come back right here with my check mark and rewriting that. I think what this is giving me is that 3 minus 1. I can't read the original matrix. Is that a 2, negative 1, 0? This is an augmented or as a matrix times my v bar is going to be equal to 0 vector. You guys, I never write this myself. You know what I really write? It's just an augmented matrix. But at least you can see where the augmented matrix comes from. And I think my augmented matrix looks just like my original A with 1 subtracted off the main diagonal. And I'm going to solve that underlying system for V1 and V2. That's not V1 to V2 bars, it's V1, V2. Those are components of my first eigenvector. And I maintain this transforms into this equivalent augmented matrix. That means the corresponding eigenvector corresponding to lambda being equal to 1 is nothing more than this. Actually, I'll be quiet. You tell me what it is.
I'm confused by the answers.
Oh, really? Go read the first row of this augmented matrix. Doesn't it say that V1 plus V2
Equals 0.
equals 0 where? V bar is equal to V1 or V2.
Yes.
So what are the eigenvectors for 1?
V1 and negative V1.
Or how about just 1 and negative 1? Times something.
Yes. So you have infinitely many eigenvectors.
I really do, but notice something very interesting about how I'm writing my answer. Notice how I said t is not equal to 0. The 0 vector cannot be an eigenvector. So help me with this. If you consider the set of all eigenvectors corresponding to that eigenvalue of positive 1, does that form a subspace of R2?
No, because we do not have 0.
No, because I don't have the 0 vector. Now, for me to find the corresponding eigenvector corresponding to the eigenvalue of positive 2, can I just not write all this garbage? I think subtracting 2 off the main diagonal, augmenting it with a 0 vector in R2, is simply going to give me a 1, 2. So that a negative 1 minus 2? But this reduces to this augmented matrix. Oh shoot, you guys, but that means the corresponding eigenvector is going to be,
One.
or better yet,
Negative 1/2.
blood is rushing out of my arm.
1/2.
You said 1, 2.
Negative 1.
That works. I thought you were going to say like 2, negative 1. It looks nicer.
Yes.
Or maybe negative 2, positive 1. And so my eigenvectors look like this times s, where s is not equal to 0. By the way, you guys, can I now use subscripts? I got 2 eigenvectors. Can I think of this as the first eigenvector? Here's the second one. And can I think of this as individual eigenvalues, lambda 1 and lambda 2, just to be consistent? So, everybody, if I were to consider the collection of all linear multiples of the first eigenvector, is that 1, negative 1? I want a yes or no answer. Does that give you the collection of all eigenvectors corresponding to lambda 1?
Yes.
Doesn't?
Yes.
Oh, you're right, it does. Does it give me more than that?
Yes, because you have to specify that you don't have the 0 vector.
I didn't.
So you should.
I don't want to.
Why?
No. Because if I now throw the 0 vector in, I give this a name. I call it the corresponding eigenspace. But the eigenspace is not the same as set of all eigenvectors because the eigenspace contains one more entry, namely the 0 element of R2. Michael?
For B2 at the bottom,
Yes.
what is the thing to the right of it? Is it
S, sorry, is times S. Just like I had times T in my last collection of eigenvectors.
Okay, so that's implied that for all S.
Not equal to 0.
So 1, you're guaranteed that the set of all the eigenvectors will always make an eigenspace. Are you?
Say that one more time, I'm sorry.
Are you guaranteed that given some lambda, the set of all eigenvectors corresponding to that lambda will always form a vector space
If you-
plus the 0 element?
Yes, I agree.
Okay. The second thing is, why do I care about an eigenspace?
Well, the original matrix is a 2 by 2. So the v-bars are all going to live in R2. And if I have 2 linearly independent eigenvectors, which by the way I do, then those 2 eigenvectors are going to span the entire space R2. Oh, they will.
Yes.
Now, given an n by n dimensional matrix, it may not be the case that I generate n linear independent eigenvectors. And if that's the case, I'm in trouble. I'm going to have to start creating some other vectors to get all the space manic. And I maintain if an n by n matrix does not contain n distinct eigenvectors, I will subclassify that matrix as being defective. But if I got an n by n matrix that has n distinct eigenvectors, I will say that the matrix is non-defective. So when I actually put this to practice later on, I get a defective matrix. I'm going to have to really start panicking, worry about a technique to generate all the corresponding solutions to my system of differential equations. So non-defective or defectiveness is going to be a big concern for you and I when it comes to solving systems.
Sounds hard.
Well, no, I don't mean it to be. I'm just saying it's not quite as natural, not quite as immediate as if I have a non-defective matrix. That's all I meant. And same question. You guys, I've only got 20 minutes left. All my questions are the same. Can you just give me the eigenvectors and corresponding eigenvalues? That's it. And maybe I could just pick a couple of them and just run with it. Maybe not. We'll see how it goes. So, if I'm going to try to find eigenvalues, I think all I'm gonna do is list my characteristic equation, which is nothing more than the determinant of A taking lambda off its main diagonal, set it equal to the real number 0. And so I think the corresponding determinant I generate when I subtract lambda off the main diagonal is simply going to be this. Now, listing my cofactor expansion about the first row, I get the first entry times what 2 by 2 determinant?
3 minus lambda is 0, 0.
Oh, so many times 0.
Aren't we experts in chapter 3?
About the-
Yeah, let's look at a cofactor expansion about the third row or third column, I don't care which. I think that's merely going to give me my lambda minus 5 times this 2 by 2. But I think that's merely going to give me my lambda minus 5 times, I don't know, is that a lambda minus 3 quantity squared? Is that a minus 4?
No, it's 3 minus 9.
True, but I had 2 of my switched. 2 negative, make a positive 1. Notice I switched this one as well. Which I can, because in a sense that means I'm multiplying both sides by negative 1. I just like my lambdas out front if I can get them there. And I think that gives me lambda minus, lambda minus 5. You guys continue to make me do all the work. Is that a plus 9? Plus 7? I'm too tired. Is that right? You guys are just staring at me.
Oh, come on.
Is that okay?
Yeah.
Okay, one yes. That means lambda is equal to negative 1. Oh, I just gotta hold it. My first eigenvalue is negative 1. My second one is going to be positive 5. I don't know why I'm going this order. It's kind of silly. Doesn't make any difference what the order is. I think lambda 3 is going to be whatever's left over. Let's check it out. I'm going to build a system of linear equations, but rewrite it as an augmented matrix by going back to that very first equation that I had before, which was A minus lambda times I times B bar is equal to 0 bar. I'm just going to write that as a system of equations. And I think if I do, it simply tells me that I'm subtracting this lambda off the main diagonal of my matrix. That's going to give me a 4, negative 2, 0, 0. It's going to give me a negative 2, 4, 0, 0. Did I write that correctly?
I don't think your factoring was correct.
No,
Say it again.
I don't think your factoring earlier was correct.
We have 9
I think
minus.
it's,
lambda
Oh.
minus 1, lambda minus 5.
yeah.
So it should be lambda minus 5 squared and lambda minus
9 minus 4 is 7.
Sorry.
So you get a lambda squared of minus 6 lambda plus 5?
Plus 5, yeah.
Ay, ay, ay. Is that a minus 1?
And then minus 5.
I'm so sorry. I apologize.
I just used difference to squares. I think that was the faster way to do it.
Wasn't even thinking that. You're absolutely correct. Difference of 2 squares works so much faster. So give me that. And I maintain it's going to change things down here. Does that give me a, ay, ay, ay. Is that a 2, negative 2? 0. Does that give me a negative 2, negative 2, 0, 0, but also a 0, 0, hold on a second. Is that a 4, 0? You guys, can I cheat? Doesn't this reduce immediately down to the following? Do you guys agree?
No,
Oh, why not?
I don't think the second row is a linear combination of the first.
Man, did I make another mistake?
Yeah.
Sorry. Now do you believe me?
Yeah.
You guys aren't going to trust me anymore, are you? Can you give me the corresponding eigenvector if you want bar? Just at a glance. Very nice. Michael?
Where do the V1 numbers
Well, if you look at this very first row, doesn't it say V1 minus V2 is equal to 0? But the second row says that V3 is equal to 0. And if my vector V1 bar looks like a V1, V2, and V3, certainly the third slot has to be 0. But if you add V2 to both sides, don't you see that V1 and V2 are going to be the same? I just drew the V1s.
Okay.
Now, I think the collection of all eigenvectors is going to be this thing times, I don't know, times R, where R is not 0. But that's one eigenvector, corresponding to the eigenvalue lambda 1. And if I take a peek at the other eigenvalue, can I give myself a little bit more room? Let's see what happens. If I subtract 5 down the main diagonal, does that give me a... Is that a negative 2, negative 2, 0, 0? Also a negative 2, oh look at that, negative 2, 0, 0. And then a 0, 0, 0, 0. What does that tell me?
There is no eigenvector for this lambda value?
Well, I think there is.
1 and negative 1. Yeah, so 0.
Well, you have two.
I have 2 of them.
variables, yeah.
Thank you.
Wait, what?
0, 0, 1.
Very nice. For that one eigenvalue, there are 2 corresponding eigenvectors. As a matter of fact, I would say the algebraic dimension of that lambda value being positive 5 is 2. But the geometric dimension is going to be 2 as well. Chris?
How did you get the second vector?
Well, I s-
I'm sorry, where you say B3 was 0, 0.
Let's see what I just go back to this augmented matrix. Can I cheat real quick?
Yeah.
Here's watch. If I were to reduce this,
Yeah.
isn't that what I can? And let's talk about what the very first row says. Doesn't it say if V2 bar is equal to V1, comma V2, comma V3, then I think technically speaking, that first equation says V1, negative 2 times V1 minus 2V2 is equal to 0.
Why wouldn't you just eliminate the negative 2's?
I forgot to.
Okay.
You're right, I think it would look better.
I mean, it
If
doesn't
I
really
complete
matter,
versus
it just,
1, 1,
yeah,
0,
it just,
It gets the same result though. So don't you guys agree that if V2 is equal to T, then V1 is equal to negative T? Oh shoot, I forgot something, darn it, V3 was,
Anything?
thank you.
Oh, I see.
And so I think my V2 bar, technically speaking, is really a combination of S times 1, negative 1, 0, plus T times, if I generate all of them, 0, 0, 1, did I do it backwards? Sorry, I did it backwards, who cares? Doesn't really make a difference in the end. But then I said, oh, excuse me. I said, let's not worry about the S and the T's. Let's not worry about the linear combination. Let's look at the basic underlying vectors. And I think the basic underlying vectors are going to be, well, this one and this one. So can I change names? Not V2 anymore. I'll just say V2 bar is equal to one of them. V3 bar is equal to another. Nothing more. By the way, in the end, how many distinct eigenvectors did I really have?
3.
And I think the set of those 3 vectors is a linearly independent set. And since the original matrix was 3 by 3, and I got 3 linearly independent eigenvectors, I will still classify, if you guys don't mind, the matrix, the original matrix A, as a non-defective matrix.
So,
Why did we decide to leave out the S and T and all that on these and all of that?
Because I did a poor job asking the question. My question is this. For each eigenvalue, can you give me a corresponding collection of eigenvectors? I didn't ask for all of them, nonetheless. In my first example, I was assuming I wanted to generate all of them.
do we have anything analogous to the rank-nullity theorem when we talk about eigenvectors? Or do you think we're gonna get
Unfortunately not. That's why I'm saying sometimes my matrix will be defective, sometimes it won't be. I've got to worry about that. You guys ready for some water?
Mhm.
Is it gonna be different with these?
I hope so. You You guys, in this example, find the eigenvalues and give me a corresponding eigenvector for each eigenvalue. That's it. Don't give me all of them. And I think when it comes to eigenvalues, you guys, I hope with even though there's only a few examples, it's enough to really start running with this. My characteristic equation is nothing more than an equation generated by looking at the determinant of this A with a lambda subtracted off its main diagonal. Set it equal to 0. I think that gives me lambda minus 3 times lambda minus 1. Plus 3 being set equal to 0. But that gives me lambda squared minus 4 lambda. Plus 6 being set equal to 0. But I don't think this particular characteristic polynomial factors nicely. So if I give up and use my quadratic formula, I come up with a positive 4 plus or minus the square root of 16 minus 4ac. Is that 24? All over 2a. Or shall I say, lambda is equal to 2 plus or minus, you guys, it's just because I'm tired. Is it a root 2?
Root 2.
I agree. Just double check my arithmetic.
Can we have that?
Huh?
Why not?
Complex okay.
Absolutely.
Well, we had a completely real matrix.
Ooh, I think that's irrelevant.
Oh my gosh.
That's, Chris, you just asked, is it going to be a similar example? No, constant. So let's find the corresponding eigenvectors. Well, the one corresponding to my first eigenvalue of 2 plus root 2 times I, I'll build myself a system of equations. I'm just going to write it down as an augmented matrix. And I think taking this one eigenvalue, subtracting off the main diagonal of A, isn't that going to give me is that a 1 minus root 2I? 1. Negative 3. Is that a negative 1 minus root 2I? Now to reduce this matrix, if I multiply the first row by multiply by
1 minus 2i. I'm sorry.
it's just work. I'm tired. Do you guys agree that if I were to be able to reduce this matrix to this, I'm done. I get the eigenvectors is
It's not.
the 0 vector?
Which
An R2?
eigenvector?
Oh, that's a contradiction. Eigenvectors can't be the 0 vectors. So it better be the case that one row is a multiple of the other. Let's see if it is. I might have made a mistake. You know I make mistakes. To see if I made a mistake, let me just see if one row is a multiple of the other. And I'm tired. I don't have any time on the clock. I'll be sophisticated. What would you multiply 1 by to get this? The thing on the bottom.
Yeah.
So we just would check to see if this entry times the same constant factor gives me negative 3. And if it does, then I recognize the second row as being a multiple of the first, and I'll stop.
Well, that's negative 1 times the first one times the conjugate of the second.
There's no conjugate here.
Like you.
Oh,
you-
pure coincidence. Don't look at that.
Oh,
I was saying this. What do you multiply 1 by to get this?
okay.
That above my hand. I'll take that above my hand and multiply this, see if I get negative 3. And so, well, technically speaking, it's not conjugates. I would have changed the sign of the second term. Anyway, if I multiply out, here's the first times the first, plus the outside times the outside, plus the inside times the inside, plus the last times the last. I can't do it. The last times the last is 2i squared, but I squared is negative 1. But it didn't work. What happened?
Your first one is negative 1, your first,
Oh, I missed it.
Yeah.
That is negative 1, isn't it? My apologies. Thank you. So I think it just verified that the second row is a duplicate of the first. So I think I've got the mathematical legal right to say that when I reduce this matrix, it becomes this. Now to come up with a corresponding eigenvector, don't you think if I just simply multiply this by 1, this by 1 minus 2i that's negative, it's going to give me 0 over here? So I think the corresponding eigenvector v1 bar, you guys tell me if I'm walking too fast, ends up being nothing more than, jeepers, is that a negative 1? And then a 1 minus root 2i? Michael?
What's the negative, or the position of negative 1? What is that representing?
A lot. You know, if I were to technically speak and rewrite this first row back in equation form, wouldn't it say this? That 1 minus root 2i times v1 no bar plus v2 is equal to 0, or shall I say that v1 times this constant is equal to a negative v2? And so I just simply maintain that if I were to refer to, I don't know, v1 as negative 1, wouldn't that give me the corresponding v2 value? That's all I'm suggesting. In fact, I think it would even look nicer if I multiplied both sides by negative 1. So to find v2, do this. Plug negative 1 in for v1. I did. But if I plug negative 1 in for v1, doesn't that give me correspondingly what's inside the parentheses as a corresponding v2 value? Now, Michael, I said a lot, and I fumbled because I don't think of it this way. To be honest with you, here's what I do. With my red pen, I just recognize to get a 0 when I add these two b's together. If I simply replace the v1 with a negative 1 and the v2 with 1 minus root 2i, the sum of these two groupings ends up being 0. I mean, in my head, that's how I generated it. But that's skipping a lot of steps. Oh, you guys, I'm almost finished. I think all I have to do now is look at the other eigenvalue and generate the corresponding eigenvector. And I think that amounts to doing nothing more than taking this eigenvalue, lambda 2 being equal to 2 minus root 2i, and subtract it from the main diagonal. And if I do, I think this is the corresponding augmented matrix I generated. Let's see, if you got the original A, would that give me a 1 plus root 2i? The 1 and negative 3 do not change. But subtracting from 1 this eigenvalue, is that going to give me a negative 1 plus root 2i? Well, you guys, here too, it's a game of seeing whether or not one row is a multiple of the other. And I think the easiest thing to do is see if the second's a multiple of the first. I think the second's a multiple of the first by, I can interpret the second's multiple of the first by seeing what happens with the second entries. What do I multiply 1 by to get this beast? Well, what's above my 2 fingertips? Now the question is this. If I multiply this entry by what was above my fingertips, do I really generate the other term down here in the second row? Well, let's crank it out. That gives me the first times the first, plus the outside times the outside, plus the inside times the inside, collapsing, plus the last times the last, which is minus 2, but that's going to give me a negative 3, thank goodness, negative 3, which is what I want. And since, I'm running out of room, can I erase this? And since the second row clearly is a duplicate of the first, can I continue to erase? I think that's what I am. But I think that necessarily implies the corresponding eigenvector, I'll call it v2 bar, is going to have entries of, I don't know how you guys want to list this, how about a negative 1? 1 plus root 2i. So it's a complex value vector. So be it. Chris?
Is it always going to be the case that if you have complex eigenvalues, then you're going to have the duplication with
Well, technically speaking, only if these entries over here are real numbers. Now, if you allow the entries in that 2 by 2 matrix to be complex numbers, then all bets are off in terms of matching up as complex conjugate pairs. But of course, my example is kind of nice. These are real entries. And so those eigenvalues will come with complex conjugate pairs.
If we have a matrix